So this video is on part 2 of section 1.4. And if you remember, 1.4 was on continuity. This lesson is on intermediate value theorem, which is a very important theorem. It will definitely come up on the AP exam. And you need to know when it's be able to recognize when it's being applied. So the intermediate value theorem is a pretty simple theorem. Like it's kind of a, well, duh. But it says if f is continuous on a closed interval, so I've drawn a picture here to kind of make sense of this. So if you have a function that is continuous on a closed interval from a to b, where the function values at the endpoints of the closed interval are not equal to each other, so f of a is not equal to f of b, then k is any number between f of a and f of b. So I'm going to pick some value between f of a and f of b on the y-axis. So I don't know, let's say here. So we'll say that's k. So k is any real number between f of a and f of b. Then there is at least one number c in the interval from a to b. So at least one x value from a to b such that f of c is equal to k. And we can see that that is true. So if I were to draw a horizontal line for this graph, we can see that this point, right, could be c comma f of c, which would be k. Sorry, I should have written that as c comma k. Or this point over here could be c comma k. We could call it about d comma k. Right, but it said that there would have to be at least one number. And this, for this picture, there ends up being 2, but there would be at least one x value that would correspond to that value of k. So in other words, the intermediate value theorem states that for a continuous function f, if x takes on all values between a and b, then f of x must take on all values between f of a and f of b. It's an existence theorem. It doesn't tell us how to identify c. It just tells us that c has to exist based on those conditions holding. So if the condition that the function is continuous on a closed interval and the endpoints in the interval, the function values at the endpoints in the interval are not equal to each other, then intermediate value theorem can be applied. So a function that's not continuous does not necessarily exhibit intermediate value property. Like this, it could happen, like for a function value that you're looking for could exist, but because the condition of the function being continuous doesn't hold, intermediate value theorem, like you wouldn't reference it. So what can we use this theorem for? So at the pre-calc level, intermediate value theorem is usually talked about in how to locate or help locate zeros of a function that's continuous on a closed interval. So remember, 0 is an x value that would make the function value equal to 0. So I've drawn a picture here, but basically, if you have a function that's continuous over a closed interval and the function values at the endpoints are different signs, like if f of a were positive and f of b were negative, like in this picture, then you know that there has to exist at least one 0 between a and b, right? There would have to be at least one x-intercept between a and b if those function values at the endpoints were different signs. So an example of that, this is straight from the textbook, but I wanted to talk you through it. So use intermediate value theorem to show that f of x has a 0 on the interval from 0 to 1. So the way that we would do this is we would want to see what f of 0 and f of 1 are. So f of 0 would be -1, And f of 1 would be 1 plus 2 minus 1, so 2. So we can see that since f of 0 is negative, f of 1 is positive, there has to be at least 1 0 on the interval from 0 to 1. Sorry. So the way that we would write out our justification here is we would say something like, since f is continuous on that interval from 0 to 1, and f of 0 is less than 0 and less than f of 1, then by the intermediate value theorem, we can say something like there exists an x such that f of x equals to 0. Or you can just restate that f has a 0 on the interval from 0 to 1. There exists x such that f of x equals to 0 on 0 to 1. Something like that. But it's important to restate that precondition that the function has to be continuous on the closed interval. And then you want to state this inequality here, and then by the intermediate value theorem, and then you're kind of restating the question. Okay, so given the function, we're going to do another similar type problem. This isn't for a 0, but given the function f of x, show that f of c is equal to 5 on the interval from 1 to 3. Now notice, it wasn't stated that this function is continuous, but you guys know that f is a polynomial function and is therefore a continuous function. So we can get started by just finding the function values at the endpoint. So f of 1 ends up being 6. F of 3 ends up being 4. You can double check my arithmetic. Okay, so we're trying to prove that there's a function value of c that makes the function equal to 5 on that closed interval. So we would say, since f is continuous, and we can tap into our prior knowledge, we know this is a continuous function. We don't have to do any extra work to show that. We know it. On 1 to 3, the interval from 1 to 3, and f of 3 is less than 5, and 5 is less than f of 1, right? 5 lies between the function, those two function values. By the intermediate value theorem, there exists a value c. I'm going to restate that inequality. Now for that inequality, the endpoints wouldn't need to be included. I'm going to include them because that was part of like giving us the closed interval. But we know that c isn't going to be 1 or 3 because we know what those function values are. Such that f of c equals to 5. Okay, something like that. Okay, so another application of intermediate value theorem. So if you measure the outdoor temperature of your backyard to be 49 degrees Fahrenheit one morning at 8 a.m., then measure the temperature at the same spot again 4 hours later to be 70 degrees Fahrenheit, Explain why there must be a time between 8 a.m. and 12 p.m. where the temperature in your backyard on that day had to be 56.75 degrees Fahrenheit. Exactly. Based on the two readings, is there a way to determine the exact time the temperature was 56.75 degrees Fahrenheit? Why or why not? So first of all, why would there have to have been a time whenever the temperature was 56.75 degrees Fahrenheit? Well, the temperature, like if we were to think about temperature as being a function of time, temperature would be continuous, right? There's nowhere that the temperature is going to like not exist. So since at 8 a.m., the temperature is 49 degrees. So you could almost think of this as like T of, if you want to let 8 a.m. be 0 times 0, would be equal to 49 degrees Fahrenheit. And then 4 hours later at 12 p.m., so like T of 4 would be equal to 70 degrees Fahrenheit. That means that there would have to be a time between over that 4-hour interval, such that the temperature would be 56.75 degrees Fahrenheit exactly. Now, there's not a way, remember, intermediate value theorem tells us that there would have to be a time that would correspond to that temperature, but it doesn't tell us how to determine that exact time. So no, we don't have a way. We could kind of estimate, like we could create smaller and smaller intervals, like try and kind of guess, but like over 4 hours, that's a pretty large period of time. It would be very challenging to kind of try and whittle that down to finding the time that corresponds to that temperature. So no, you cannot determine the exact time, but we know that there would be a time such that the temperature would be 56.75 degrees Fahrenheit in your backyard. So you can say something like, since temperature is continuous, I'll just say, since temperature is continuous from 8 a.m. to 12 p.m., and 56.75 degrees Fahrenheit is between, and you can use greater than or equal to or less than or equal to, it doesn't matter. I'm going to put strictly greater than 49 degrees and strictly less than 70 degrees Fahrenheit by the intermediate value theorem. And then I'm going to state by the intermediate value theorem, there must be a time between 8 a.m. and 12 p.m. such that the temperature is 56.75 degrees Fahrenheit. Okay, so this is a piecewise function. Determine if intermediate value theorem applies on the different intervals that I've given. This is a pretty complicated looking piecewise function, but we think about those preconditions for intermediate value theorem. The function has to be continuous. and defined on a closed interval. So we want to determine whether or not f of x is continuous on these different closed intervals. So -4 to -2. I already see a typo. This should be x less than or equal to -2. So -4 to -2. -4 would be up in this first interval, and then -2 is included in that first interval. So yes, and -2x plus 1, well, that's just a line. That's going to be continuous. So intermediate value theorem would apply. So explain why not. So f is continuous on the interval from -4 to -2. Therefore, IVT applies. Okay. I don't think they're all going to be so easy. -3 to 0. -3 to 0. Okay, -3 would be on this first interval to 0, and 0 would lie on this interval, right? -3 and then up to 0. So there is a potential point of discontinuity looking at the two functions. Both of those pieces, both of those functions for the first and second piece are continuous over their implicit domains of all real numbers. So the only potential point of discontinuity would be at -2. So we want to think about left-sided limit. So limit, well, first of all, function value. So f of -2. F of -2 would be plugging into that first piece. So we get 5, and then the limit as x approaches -2 from the left would be 5. And the limit as x approaches -2 from the right would be also 5. So two-sided limit would be equal to 5. That matches the function value. So yes, f would be continuous on that closed interval. So f is continuous on the interval from -3 to 0. Therefore, intermediate value theorem applies. Okay, -1 to 1. -1 to 1. Oops. Okay, -1 would lie on the second interval to 1. Well, it looks like 1 is a potential point of discontinuity. So we would need the limit as x approaches 1 from the right to match its function value. So f of 1 in this case, I'm going to do my work up here. So f of 1 would be 3, because 3 times the square root of 1 would be 3. And then the limit as x approaches 1 from the left, we would plug into that second piece. So we'd get 1 squared plus 1 would end up being 2. Okay, so the function value does not match that limit. Therefore, 1 would not be part of the interval, right? So 1 would not, the function would not be continuous at that endpoint, and therefore intermediate value theorem would not apply. So f is not continuous at 1. Therefore, IVT does not apply. Okay, 1 to 4.5. 1 to 4.5. So 1 is included in this interval, and then up to 4.5. So 4.5 would be in this last piece here. Okay, so 1 to 4. Okay, so 4 is a potential point of discontinuity. So we want to make sure that the function would be continuous at 4. So f of 4 would be 6. And then the limit as x approaches 4 from the left would be also 6. And then we know that the limit as x approaches 4 from the right would be 6. That two-sided limit then is equal to 6. So the function value matches the limit value. So the function would be continuous. And then we know in this last piece that 5 would make that discontinuous, right? There would be a vertical asymptote at x equals to 5. But since the endpoint of that interval is 4.5, we're good. So f is continuous on the interval from 1 to 4.5. Therefore, IVT applies. Okay, last one. Oh, we already kind of answered this. I know this isn't true. So it says from 2 to 7. Well, 2 is in this interval, this third piece, but when x is equal to 5, we know that there's a vertical asymptote. And 5 lies on that interval. So f is not continuous at x equals to 5. Therefore, IVT does not apply. Okay, so the velocity of a particle, we're going to talk a lot more about particle motion, but we need to study derivatives first. But the velocity, this could maybe be one part of like a free response question. So the velocity of a particle moving horizontally along the x-axis is given by the continuous function v of t. T is measured in seconds. I should say seconds. And v of t is measured in feet per second. Selected values of v of t are given below in the table. Explain why there must be a time on the interval from 2 to 5 where the particle is at rest. Okay, so v of t represents the velocity of the particle. The positive or negative velocities indicate direction, remember, because velocity is a vector quantity that has both magnitude and direction. So those are 4 different velocities at specific times that have just been chosen. So we want to explain why there must be a time on the interval from 2 to 5 where the particle is at rest. So between 2 and 5. Now, the velocity of the particle, give me continuous function. Continuous function. Okay, so we're thinking about the closed interval from 2 to 5. And I realize it says an open interval here, but that's just saying that there must be a value of t between 2 and 5. We can see what the velocities are at 2 and 5. So there must be a velocity between 2 and 5, not including 2 and 5, where the particle is at rest, meaning that the velocity would be 0. Okay? And since v of 2 is negative and v of 5 would be positive, that means that yes, there would have to be a velocity equal to 0 between t being 2, 2, and 5. So to write this out, we can say something like, since v of t is continuous on, you can either use interval or you can use an inequality notation. And v of 2 is less than 0 and 0 is less than v of 5 by IVT, there must exist a time on the interval from 2 to 5 where the particle is at rest. Or you can say something like v of t would be 0. Okay, so this is actually this is modified from an FRQ, a part of a FRQ from the 2007 AP Calculus AB exam. So the functions f and g are continuous for all real numbers. The table above gives values of the function at selected values of x. The function h is given by f composed with g minus 6. Explain why there must be a value r for r between 1 and 3 such that h of r equals to -5. So it's just asking for the existence of this function value. That's kind of a ding, 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 intermediate value theorem. So we're given a continuous function, right? Since f and g, so h is made up of f composed with g, f and g are both continuous for all real numbers. That means f composed with g would also have to be continuous over all real numbers, and then -6. That still makes it continuous. So we need to explain why there must be a value r for r between 1 and 3, such that h of r is equal to -5. So we need to basically figure out what our first go-to is, to figure out what the function value would be at the endpoints of the interval. So at 1 and at 3. So we need to figure out what h of 1 would be, which this is kind of the trickiest part of this problem. So h of 1, I need to first think about, since g is the inside function, I need to figure out what g of 1 would be. G of 1 would be 2. Well, then that means we're evaluating f at 2. So I go back over to x being 2. F of 2 would be 9. 9 minus 6 is 3. Then we want to find h of 3. So we need first g of 3, right? Since g is the inside function, so that would be 4. So that means we're evaluating f of 4. So we go over to the x value of 4. F of 4 would be -1. -6 would be -7. Well, -5 lies between -7 and 3. So, yes, there would have to be an r. Well, it's not asking us, it's asking us to explain why. So, we'll do that. So we can say, since h, didn't finish writing out since h is continuous, it says for all real numbers. So I guess we could say, it says h is continuous for all real numbers. So we could say, since h is continuous from 1 to 3, since it would be continuous for all real numbers, and h of 3 is less than -5, and -5 is less than h of 1. So we're going to write that inequality by intermediate value theorem. Now I'm going to kind of restate the question. There must be a value r for r between 1 and 3 such that h of r equals to -5. And voila. Surprise, surprise, I have the grading rubric. So we can see this. Here's where the points come from. So the grader is looking to make sure that you have h of 1 and h of 3 shown in your work. And then they also want you get a point for your conclusion using IVT. So you don't actually have to state IVT, but the preconditions have to be there for IVT being applied. So in their sample response, right, h of 1's there, h of 3, since h is continuous, and since, I guess we could have just said h being continuous. I restated the closed interval, but I could have just said since h is continuous over all real numbers, or since h is continuous. When you see a function, like them stating that a function is continuous, that means it's continuous over all real numbers. Like it's continuous everywhere. So they just stated in a different order, h is continuous, and then that inequality, right, that -5 is greater than h of 3 and less than h of 1. By the intermediate value theorem, there exists an r, where r is between 1 and 3, such that h of r would be equal to -5. So you have to have some sort of, it is important to state that h would be continuous, and then that inequality that states that that function value would lie between the two endpoint function values.